Welcome to Lecture 13. We are wrapping up Unit 2 this week with the topics we cover in this lecture set and the next set. In this set, we do a conceptual coverage of rotation topics. When you look at Chapter 6, Rotation, you will see a resemblance between what we covered this week and what we have covered in mechanics so far. We are going to start with a form of kinematics, that is a study of motion, and we will introduce something that is related to mass, that is inertia in the rotational context, rotational inertia, leading to a discussion of Newton's second law. And all these resemblances are tied together in what we call an analogy between translational motion and rotational motion. In Rotational Analog section of the lecture, this connection will be made explicit, and we will use this as a shortcut of sort to get to rotational kinetic energy and rotational angular momentum. In the rest of the lectures, you will see some demonstrations of angular momentum. You will see situations that conserve angular momentum. I'm going to stand on a rotating platform and do things that illustrate how angular momentum is conserved as different processes take place. And you will see an example of precession, which it doesn't conserve angular momentum, but the counterintuitive motion you see in the precession of a bicycle wheel can be explained through how torque changes angular momentum, analogous to how force changes the momentum. The very last section in this lecture deals with an essay assignment that we used to have. If you are interested, I do encourage you to search the Veritasium video you will see mentioned in the section. I do have my own demo of bicycle wheel precession in earlier videos in this lecture set, but you might want a more in-depth explanation as done in the Veritasium video. In the next lecture, we will look at topics relating to fluid mechanics to wrap up our Unit 2, Mechanics 2. Hi, this is the overview video for Chapter 6, Rotation. There's a way in which a lot of things you will see in rotation is a review. It's a review of the mechanical and dynamical concepts that you have seen before. So we'll start out with the kinematics. And in angular kinematics, you are going to see angular version of different kinematical things that you have seen earlier in Chapter 1. We'll introduce radians, the unit of angle, as a way to measure angular displacement. Radian is defined as arc length divided by radius. And in my Physics 4A class, I like to emphasize that this is a non-arbitrary way to define angle. Unlike degrees, where frankly the 360 degrees being a full circle, it's arbitrary. We could have made it 100 degrees or something. But in radians, the fact that the radius of a unit circle of radius 1, is 2 pi, that's not an arbitrary thing. So, but in this class, our coverage will definitely be conceptual. So these quantitative emphases are not as important. What I do want to emphasize is that we start by defining angular difference that will be measured in radians for most formulas to work correctly, and that's defined as the arc length divided by the radius of the circle that the arc length is part of. Once you have the angular difference, angular displacement defined, then you can talk about angular velocity, which looks at how quickly that angular displacement is changing. It's the rate of change of angle. The way velocity was rate of change of displacement, rate of change of position. The unit for angular velocity is what you would expect it to be. It's the unit for the angle, radians, divided by second. And one thing to be careful about the radian as a unit, it's not a quote-unquote real unit. You can kind of see it here in that arc length, it's a distance, it can be measured in meters, and radius is also a distance, it can be measured in meters. So when you take this ratio, the ratio is unitless. So we say the word radian when we want to remind ourselves that we are talking about angular quantities. So angular velocity, sure, properly that's radians per second, but in so many circumstances you might see this radian omitted. Or sometimes there's a factor of 2 pi that turns that into cycles rather than radians. Again, we are treating this conceptually, so we'll stay away from a lot of those situations. And this angular velocity can be related to the velocity, translational velocity, or tangential velocity. That relationship is here. The v, tangential velocity, is equal to r, the radius of curvature or radius of the circle that this arc length is part of, that r times the angular velocity omega. That's this letter. It's the Greek letter lowercase omega. So this v is equal to r times omega. That's the relationship that relates the angular velocity to the corresponding tangential velocity. I think the main intuition I want you to get is this dependence on the distance. In the lectures that I'm borrowing from Physics 4a, actually, you will see some physical illustration of that with a turntable. And finally, angular acceleration. It's defined in a similar way acceleration was. It's the rate of change of, so for acceleration that was velocity. For angular acceleration, it's rate of change of angular velocity. And unit is the way you'd expect it to, unit for angular velocity, divided by second again, so radians per second squared. And there's a matching relationship between tangential and angular acceleration, the same way as tangential and angular velocity. And with the angular acceleration, I guess one thing that I'll caution you about is don't confuse it with the centripetal acceleration. Angular acceleration is related to the tangential acceleration, the acceleration along the circle, the periphery, the circumference of the circle. The centripetal acceleration that we mentioned earlier, it's an acceleration that's perpendicular to the circumference of a circle or the radial direction. Just beware that angular acceleration is distinct and different. It's orthogonal to, in some sense, to centripetal acceleration. So that's the rotational kinematics or angular kinematics. And just with the chapter 1 material, this is probably the most mathematical part of chapter 6. Although in terms of your homework, you won't see that many any calculation questions. So, don't let those math equations scare you. And we walk through the rest of dynamics, mechanics, the way we did from chapter 1 to chapter 2. In chapter 2, we introduced the force. So now, in the context of rotation and rotational dynamics, we have quantities that are the counterparts to the force and mass. And those are torque and rotational inertia. In the lecture videos, you are going to see rotational analogs that will make this connection more explicit. Torque is to force, the way rotational inertia is to mass. So now torque is related to force, and there's some formula for that that's described. So torque, like a force, it causes motion in some sense. So force causes acceleration to happen. So torque causes angular acceleration to happen. It can be a measure of turning effectiveness. And torque, indicated by this Greek letter tau, lowercase tau, that's related to force this way. The torque is given by lever arm, letter R here, lever arm times the force. And there's a mathematical operation that we do called the cross product. I'll go back to that near the end of this overview video, and there are some examples you can look at, but it's the kind of thing where if that's confusing you, you can totally just skip it. It's not all that important to the rest of the things we are doing. But torque, it's given by product of lever arm and force, and the unit of torque, it's just Newton times meter, unit of force times unit of distance. Sometimes it might look like it's a joule, unit of energy, but please don't mix them up. Torque is not energy. We'll talk about energy in a little bit. Rotational inertia, that's the counterpart to mass, to inertia. So it's resistance to rotation, the way inertia was quote-unquote resistance to motion or change in the state of motion. I guess all of this makes much better sense once we get to Newton's second law. And as we are getting there, the formula for rotational inertia is it's some form of mass times distance squared. Now it does depend on mass distribution, so it can be a little bit complicated for rigid bodies that are not point mass. There's a table of rotational inertias in the textbook, and again, our coverage is mostly conceptual, so you don't have to do calculations with those. But there are homework questions that are asking to rank different things based on whether different objects have greater rotational inertia or smaller rotational inertia. So do look at that table and make sure that it makes sense. There's a lecture demo with a disc and a ring rolling down. Make sure that result of that demo makes sense to you. And finally, the torque and rotational inertia are defined in a way that we recover something that looks like Newton's second law in the rotational context. And so you remember, let me just zoom out a little bit so that this fits a little bit better. So you remember Newton's second law in the translational context. Net external force is equal to mass times acceleration. So the rotational version of Newton's second law reads net external torque, which is replacing force, is equal to rotational inertia, which is replacing mass, times angular acceleration, which is replacing acceleration. There's a one-to-one match between the rotational quantities you see here and the translational quantities we looked at back in chapter 2. Both are Newton's second law. In lectures, you will basically hear me refer to Newton's second law, Newton's third law in the rotational context, assuming you can do that translation or that analogy comparison. And in the lectures, you will see me talk explicitly about rotational analogies. I think in your textbook that comes up as we cover energy and momentum. And that analogy between rotation and translation, it's really powerful because it allows to transfer or translate or use the intuition you gained in the translational context to the rotational context. So, rotational kinetic energy, you might not have any idea what that depends on, but if you remember that in the translational context, the translational kinetic energy was 1/2 times mass times velocity squared, and you remember this thing, rotational analogy, then you can almost guess at the formula for the rotational kinetic energy, which will be 1/2, that's the rotational version of 1/2, the same thing, times the rotational inertia, which is the rotational version of mass, times the angular velocity, rotational version of velocity, squared. So this formula 1/2 I omega squared, you could just guess it from your knowledge of translational dynamical quantities and the trust in the rotational analogy. And you can do the same thing with the momentum. So if you remember, momentum that we covered earlier is mass times velocity. For the angular momentum, you can guess, what is the rotational version of mass? Rotational inertia times what is rotational version of velocity? Angular velocity. So angular momentum is given by the rotational inertia times angular velocity, and the units match up with that. And in the translational context, after we introduced the momentum, we talked about how the true form of Newton's second law is described in terms of momentum. That force is the rate of change of momentum. Same deal here. Torque is the rate of change of angular momentum, delta L divided by delta T. And this same argument from analogy applies to conservation of angular momentum. For conservation of momentum, we looked at external force. We said if there's no impulse due to external force, then we can say the total momentum of the system is conserved. Similarly, we can say that the total angular momentum is conserved if the net torque due to external forces or external torques is equal to 0, then total angular momentum is conserved. And I have a lecture demo that shows result of this angular momentum conservation as rotational inertia is changing. Your textbook has, I guess, ice skater spinning. For the lecture demo, I don't have an ice skater, but I do have a video of me standing on a rotating platform. So that's a rotational kinetic energy and angular momentum. Oh, I guess here it just says energy and momentum. Yeah, it's you can look at this as the rotational extension of the translational things that you have already seen. So that covers the most of the chapter. There's one last section in which we look at gyroscopic effect and the right-hand rule. I do take a look at it. I used to have an essay question that kind of relied on it, looking at a precession of a bicycle wheel. I don't have those essay assignments anymore, but you will see a lecture video that's just a question and answer about that precession. And within that video, you will see reference to the Veritasium video. So if you are interested, you can search up that video and look at it on your own. What I will say is that do take a look at the textbook section, see if it makes sense to you. If it does, great. I hope you get something out of it. If not, you can totally just skip it. It's not super important for the rest of the things we'll do. I do think it's an interesting effect that's fun to be able to, explain at a cocktail party or something. I don't know. So that's, I think, all the topics in chapter 6, rotation. Rotation is a bit of a shorter chapter, so this week we'll also cover the remainder of mechanics topics, wrapping up unit 2 this week. Thank you. Bye. So what I really want to go into today is rotation. So we are going to have to talk about rotation the same way we talked about motion. Oh, I keep bringing out this bicycle wheel because I can use this to illustrate the quantities we are talking about in rotation. So right now, this bicycle wheel is stable. It hasn't rotated or anything. Now, a moment later, has this bicycle wheel rotated? Yes? Did it move? How do you know? You look at this tape, right? It used to be on the vertical spokes, and a little bit later, it's on the horizontal spokes. Well, it must have moved. So, as a comparison, that's how we start looking at motion. So when we are looking at motion, I think this is like one of the first things I said on the first day. We look at position of an object, and the position of the object, unless we are talking about boring things like equilibrium, we are talking about where the position moves. So that at some later time, it's at some different position. So we are going to have a similar parameter for rotation. So instead of position, we are going to have an angular position. Angular position, which I guess we can mark it with the letter theta, which is the common letter you use to measure angles. So let me go over some of the peculiarities here. So let's say let me turn it around. Let's say the angular position you see right now for these tapes is 0 whatever. What is the angular position for the tapes right now? Pi over 2 in radians, or 90 degrees. So is it plus or minus? A lot of you say plus. Yeah, you might be importing your sense of direction from your geometry class, which is fine. In your geometry class, counterclockwise was positive. Starting from positive x-axis, going over to y-axis was positive. Okay, so this is pi, right? This is, okay. Now, what's the total change in angular position? Any other answers?
2 pi.
Yeah, 0 or 2 pi. Now, if you just saw this position just out of the blue, you wouldn't know which one. But imagine this. Let's say this was the initial angular position, and over time, you observe these tapes moving this way. Round, round. And somebody asks you for the angular displacement of these tapes.
2 pi.
So once again, I guess you could give multiple answers, but the most correct answer is 4 pi.
So that's one of the peculiarities with the angles, right? That it repeats every 2 pi. So you could choose to take modulo 2 pi, as in you take the thing, divide that 2 pi, and take whatever the remainder, and say that's your angular position. And if you're talking about the position at a fixed time, that would make sense. But for the mathematical operations that we are going to do, you might want to keep the history of the thing in mind. Because maybe this angular position that I'm relating to, maybe that will be related to how far this rolls. So if I'm trying to measure, how far is this wheel rolling as it rolls without slipping over some surface, and I want you to imagine it's still rolling without slipping, and if I ask you how far did it roll, the answer is going to matter. Is this 0 or 2 pi? Or as it rolls more, the answer is going to depend on the answer for the distance is going to depend on is this 0, 2 pi, or 4 pi. And what I'm telling you is the answer of 4 pi will never be wrong, whereas answer of 0 or 2 pi could be wrong sometimes. It's some peculiarity. We don't deal with it too much, so I want to highlight it, but not spend too much time. One last question. I have actually 2 different tapes on this wheel. Do they have the same angular position or different angular position? Okay, they have different. Ali, you said same. Why did you say same?
Because they are on the same line.
Yeah, they're on the same line. Yeah. As in, what would you say is the angular position of the small tape? 0. Okay, 0. What's the angular position of both of the tapes? Pi over 2, both of them, right? Yeah, so their positions are different, but their angular position is the same. So, and we'll talk a little bit more about the relationship between position and angular position. But the starting point is angular position. It's, let me start writing it from the beginning. So it's, you could say this is defined in analogy, or in comparison, or analogy is the word I prefer the most. Analogy to the position x. And this angle theta, it can be a function of time. Just like in most interesting cases, position was also a function of time. Yeah? So remind me, when we are dealing with the motion, what did we do with the position once we defined it? Did we define anything else using that definition of position? Yeah, we defined the velocity, right? And then we define the acceleration. So we are going to define similar quantities for rotation. We have angular position. So now we are going to have angular velocity. And we are going to have angular acceleration. And when I start writing down the relationships, I hope it starts to look familiar. As in angular velocity, I would define that. So omega is the symbol I use. I'll talk about the symbols in a bit. So angular velocity, we would define that as the time derivative, or rate of change of the angular position. And angular acceleration, we would define that as rate of change of angular velocity. And I'll talk about the letters we are using in a bit. Whenever you feel confused or whatever, the picture that I want you to come back to is the linear motion. Because a lot of people have good intuition for linear motion, even when you can't do kinematics problems, but you have good intuition still. You see a lot of things moving linearly. So the angular position is analogous to position. Angular velocity is analogous to the velocity that you have seen before. And angular acceleration is analogous to acceleration that you have seen before. How many here remember what analogy means? I don't know if, how many here had to take SAT? But they took analogy out of SATs now, right? That happened many years ago. So it doesn't work. What it is the relationship. So if you have a relationship between two things, that's similar to relationship between other two things. You could say a driver of a car is to, the relationship between driver of a car to the car is like the pilot of airplane to the airplane. Now those are completely different things, but those relationships are similar. And that's really what we mean by analogy here. Angle is nothing like a position. But when you look at these relationships here, remember how we defined velocity. We defined it as rate of change of position, and we defined the acceleration as rate of change of velocity. The new relationships that we have defined here, they follow the pattern that you saw before. That's really what we mean that they are in analogy, as in they are comparable. So velocity is to position, the same way angular velocity is to angular position. Yeah. So one aspect of that is that even though we want to keep referring to these old quantities that we have defined, we want to make sure that these two things, they are not the same. The angular velocity is not the same as velocity. So that's why we have to assign different letters to denote angular velocity. And we have to assign different letter to denote angular acceleration. That's distinct from the letter for acceleration. So I think that most of it actually saw this Greek letter. So if by convention, all the rotational quantities are given Greek letters for some reason. You saw that with the torque, we use the Greek letter tau. So for position, we use theta for some reason. I think you guys actually have seen this letter before. Omega, right? And I just want you to be careful with omega. My omega, you have no excuse for confusing my omega with my W. I know some people write them in a way that they're confusing. I never do. My omega bottom is always rounded. My W bottom is never rounded. So W and omega are completely different. They're nothing like each other. Yeah? And I think alpha is pretty distinguishable from A. No A I ever write has this upper half tail. So, yeah. So these are the basic quantities we start out with when we are discussing angular motion or rotation. So when you have this, right now, what would you say is constant in the motion of this wheel? Yeah, ignoring friction. Yeah, angular velocity is constant. Its angular position is constantly changing. It's going from 0 to 2 pi, and then another 2 pi, another 2 pi, like once every second or so. So angular velocity is one thing that's constant because it seems to be rotating at the same rate. Now, would you say angular acceleration is constant here?
Yes.
Yeah, constant at 0 value. Now, what would the motion with the angular acceleration at a constant non-zero value look like?
The wheel would just increase in speed.
Yeah, so I think I find it hard to do it with the bicycle wheel, but I can do it with this turntable. And I probably should set this up at some point today. So let me do that now. All right. Good enough. So this is the way I can get constant angular acceleration. I can use friction. So I can, start moving my hand over it at some constant normal force. So the amount of kinetic friction is the same. So as I keep moving, it, angularly accelerates. I guess it's kind of hard to see on that screen, especially without a marker to use as a guide. So let me put down a blue tape as a kind of a marker. So let me put down a blue tape in one part here. And I'll try to avoid the blue tape as I angularly accelerate it. So a motion with a constant, let me do it in a way that it's going in the positive direction as seen by you. So a motion with a constant angular acceleration, constant positive angular acceleration, the way we normally define it, might look something like this. So at some point, okay, I can't rotate it anymore. But good. And all of this matches with your intuition about linear motion. Like, a linear motion with a constant acceleration would start out slow, but over time, it'll reach higher velocity. And it's the same thing here. So I guess I will tell you one thing that may be a relief or maybe not. So we are kind of going to skip rotational kinematics. But let me point out this much. So you guys had kinematics formulas, right? You had a linear, so we didn't call it linear because everything was a linear then, but you had a linear constant acceleration kinematics formulas. Everyone here knows what I'm talking about? Yes? No? The velocity as a function of time is initial velocity plus at. Position as a function of time is initial position plus v naught t plus 1/2 at squared, right? And to cap this off, the v squared formula, v final squared is equal to v initial squared plus 2a delta x. Like, all of this looks familiar, or you've seen this before? What I'm telling you is that without explicitly driving them, there's an analogous version of this formula for rotation. So I could just, from knowing all of this, I mean, I can go through the derivation all over again. It'll be the exact same derivation with the symbols switched out. But when I do, what you would get is rotation, rotational, constant angular acceleration kinematics formula. And from knowing this, I can write this down, not even from memory. I'm essentially taking this expression, and wherever I see v, I'm substituting in omega. So I can say, well, so angular velocity as a function of time is equal to some initial plus, I have to replace a with the angular acceleration. Angular acceleration times time. Time is the same for both of them. And the same thing for position. So theta as a function of time is equal to initial position plus initial angular velocity times time plus 1/2 angular acceleration times time squared. Or the v squared formula in the rotational version of them. So omega final squared is equal to omega initial squared plus 2 times angular acceleration times change of angle. Is it clear how I'm writing down all these formulas without having anything to refer to other than this? Yeah. So I'm pointing this out as a reminder that all the things you learned in kinematics, in translational motion, they still apply. All the that's why it's worth going back and reviewing if you didn't feel like you did so well on kinematics, because whatever you learned then will be useful for what we are covering now. As you are doing rotation, it'll help you to go back and review anything that you didn't get the first time around, because sometimes it just takes time for things to sink in. Yeah. So this is the start of the discussion of rotation by being able to describe where things are. So I think this might be one of the homework questions, or I might be confusing with the physics 10. So call this 100-gram mass Bob, and call this Alice, and call this 500-gram mass Bob. Then these two are at the same angular position, as you can see on the screen, right? And actually, let me make them the same mass so that you can kind of see the difference. The only two masses I have the same ones over 200 grams. So should I write their names? Okay. So the one that's on the inside is Alice for A. And one that's on the outside is Bob, or B for Bob. All right. So they're at the same angular position, right? Good. And as they move around, they remain at the same angular position. But if I start spinning it faster, something different happens with them. Let me move this away. I don't want to break anything. So as this starts to spin faster and faster, Bob slides out while Alice doesn't. Why? Like, I thought they were at the same angular position. So what was the difference between Bob and Alice? That Bob slides up, but Alice doesn't. Yeah, so Bob is actually moving faster, right? You can see that the linear velocity of Bob is faster. So when you look at this, so you can talk about the angular velocity, but sometimes you will want to talk about the velocity. So you should know how they are related. So let me call it this way. Relationship between the rotational quantities, angle, angular velocity, angular acceleration, and the translational quantities, linear motion, position, velocity, and acceleration. And if I'm being perfectly clear, as in non-ambiguous, that's usually what I mean when I say clear, anyways. I should clarify that I mean these to be tangential quantities. As in when I talk about x, I don't really mean x in the sense of, moving from here. So, I sort of put them along the x-axis, right? When I say x, I don't mean position along your imaginary x-axis. That's not what I mean. When I talk about x, I'm talking about the motion along the circle, along the periphery of circle, or what we call tangential direction. So what I want to briefly go over is the relationship between the angular quantities and the tangential motion-related quantities. Yeah? So let's start out with the velocity. I think that's the one that comes up most often, so maybe it's the most useful. So let's say I know angular velocity somehow. It's given to me, I calculated it, I measured it. Somehow I know omega. And from omega, I want to be able to calculate what velocity or tangential velocity is. What do I need? Is omega by itself sufficient, or do I need to know something else? So as you are trying to figure out the tangential velocity, the one additional parameter you need to know is the distance from the center of rotation. Let me call that r. And that's kind of why we use the word radius often for that, because we are imagining a circle that this is moving in the path of, and we are imagining radius of that imaginary circle. So let me set aside this r. So does anybody in here know, using this r and omega, what the expression for tangential velocity should be? Or let me go back to the one example for position. Maybe it's easier for position because you can visualize it better. So let's say I have a change in angular position. And from knowing the change in angular position, I want to be able to get to some kind of change in the position, but it's not delta x in a straight line. It's delta x along the circumference of the circle. So let me draw a picture to help us imagine what this looks like. So let me draw this circle here. This is my circle of radius r. And yes, someone was saying arc length, right? So what this delta x is, it is arc length. So it comes down to the question of, all right, so you know the radius r, and let's say for this particular arc, you know the angle here, delta theta. How do you express this arc length? One person Abdi, please. Yeah, this arc length is equal to, trying to color code it, r times theta. Theta I'm using, oh wait, I mixed up my colors. Okay, so Abdi, how do you remember this formula? Why is the arc length r times delta theta?
The circumference is towards the,
Well, 2 pi r?
2 pi.
Yeah. So, okay. My question was actually kind of backward. So the proper way to remember this is remember how we defined the angle in the first place. It goes back to the definition of radian that we spent some class time on. Angle itself is actually defined as the arc length divided by, so if I call this the arc length, delta x, then angle itself is actually defined. The definition of angle is the arc length divided by the radius. That's how radian is defined as angle. So once you know this, then the rest of what I'm asking for here is simple matter of doing a little bit of algebra. Solve this for delta x instead of delta theta. then you get for arc length that's equal to the radius of the circle that you are imagining times the angle, delta theta. Okay. A tangential velocity, that's a very simple formula. That's just the radius times the angular velocity. Just recall back to this, and that's just the relationship between tangential quantity and angular quantity. That is the relationship between angular quantity and the tangential or linear quantity. And this continues on from position, velocity, and acceleration. You can look at it either the same relationship carrying over for different cases, or you can look at it this way, taking this expression and just taking derivatives. When you take the first two derivatives, you get the velocity for left-hand side, and you get angular velocity for right-hand side from these relationships here, these relationships here. And then if you take another derivative, then here you get angular acceleration, which can be used to express the acceleration or tangential acceleration. So by the way, this is another thing to point out. This tangential acceleration we are talking about, it has nothing absolutely to do with centripetal acceleration. Centripetal acceleration was a radial acceleration. Now that we are talking about rotation in full, it's especially important that you don't mix up tangential with radial. It's two different directions. So tangential acceleration follows the same relationship here. This is equal to radius times angular acceleration. Okay. So these are all very simple relationships. And it's simple because it's coming from a simple definition. Okay, so this is sort of the introduction of the language that we'll be using. So, when we talked about motion, kinematics, that was the language that we used to talk about the things that we were actually interested in, forces. Then from that we talked about work, energy, momentum. Work, energy, momentum, and I guess impulse. So when we are dealing with the rotation, we are essentially retracing those steps again. So this is the language we'll use. And whenever we want to translate between what we did before, this side, to what we are doing now, then this is our translation table from the linear quantities to the angular quantities. So, and we are going to use this language to discuss the dynamics that we are interested in rotation. One of them will be torque. We talked about that last week. And we are going to bring up energy in terms of rotational kinetic energy. And we are going to bring up something called angular momentum. That will be like the Thursday before your exam. So for the rest of today, we actually have to set aside some time talking about something called rotational inertia. And in keeping with the analogy that I've been trying to emphasize, what do you think rotational inertia is similar to? Like if you are trying to find the counterpart in translational motion. So, okay, inertia maybe. What is inertia? I don't think I really used the word that much before. I could have, but okay, you could say it's similar to inertia. Well, so inertia is actually synonym for a different word that we actually do use a lot.
Friction.
Not friction. You are thinking of inertia as something that stops something from moving. That's not what inertia is. Inertia is something like in everyday language, when we talk about inertia of a large organization, when it gets moving, it actually keeps on moving unless something happens to stop it. It's related to Newton's second law or first law or whatever. So if you're treating inertia as a noun that's referring to an object or property, it's a synonym for mass. Or you could say one of the properties of mass is inertia. The second property is the one that we haven't talked about yet, gravitational attraction thing. But so rotational inertia will be similar to mass that we talked about in translational motion. So hopefully we'll have some time to talk about this as well. All right, I really do have to go over this before we wrap up the class today. Otherwise, I've written this down and I've never actually finished what we are talking about here. So we spent some amount of time dealing with the torque. And in some future class, we'll deal with some problems that are like a standard strategy. As in you analyze the net torque and that'll give you some angular acceleration. But as you try to do that, a piece of information you need to get is this quantity that's analogous to mass. And for now, I'll give you the symbol for it, and I'll give you its names. And we'll do a quick exercise that'll hopefully build some intuition for this quantity for you. So the letter we use for this is I. I guess I for inertia. But it's not inertia, because if I just say inertia, that's mass. So it's not inertia that I'm talking about. It's a particular type of inertia. And I will have to tell you that there's two different names for it. They are both commonly used. The second one that I'll give you is a little bit more old-fashioned, but I think your textbook still uses it, so you have to know both. So the word I will use most often is this, rotational inertia. It's sort of what it sounds like. It's like inertia, but it matters for rotational motion, right? And the other name that's more old-fashioned, but your textbook, I think, uses it, is this name called moment of inertia. So inertia part is clear, what we mean by that. The whole moment thing, I have no idea. All I can tell you is that it has nothing to do with the time. It doesn't have anything to do with moment of time. It might have something to do, there's a sense of moment that means some kind of weight. There's when you do like electrostatics, there's something like multiple moment or like moment of, it's an old-fashioned term. But when someone says the word moment of inertia, it means the exactly same thing as rotational inertia. And it means what we are going to refer to with this letter I. So your lab today is actually a lot about rotational inertia. You are going to be measuring some amount of rotational inertia for something. The exercise I want you to end the class with, this used to be part of a lab that, we are not doing this semester. So this is what I want you to get. Let's see, I need to pass this out in an efficient way. Yeah, could you, let me do it this way. Could you take this, pass the rest back? Let me just get one for Tikal. You will need, for each desk, you will need one full ruler. And let me pass out these wooden rulers. So these are half meter sticks. For each desk, thank you, Kiranji. So for each desk, you will need 2 of these. And yeah, could you pass out the rest? Thank you. So you have maybe a couple minutes or so. In that time, this is the sense of rotational inertia that I want you to develop. So the rotational inertia, you can get a sense of it by taking this and trying to rotate it. And your fist doing this versus actually rotating it, it does take more effort, right? Yes? Now, when you take this, when you take these 2 rulers, they have about the same mass, right? No, 2 rulers, 2 of them. Yeah. Okay. When you take 2 of them, then they have about the same mass. And I want you to try this and compare that with this. One should be easier than the other. Yeah? So, I want you to think about, why is it easier to rotate this than this? That's one I want you to think about. The other is even taking this same, 2 rulers, if you change the place where you are holding and do the same thing, it'll suddenly become harder. So, I want you to just think about, why it's harder. So, oh wait, I have 2 minutes. Okay, I think I have, so, you can do that for the rest of the class, but let me just prepare you for the lab. So for the lab, just so you know, we don't have a formula for rotational inertia yet. But what you do have is you do have a role for the rotational inertia. So here's one role rotational inertia fills. So this is the Newton's second law equation where this rotational inertia plays the same role that mass plays role. Do you know of any other formulas where mass plays a role? Give me some of the formulas where you see mass in it. Well, we already have that. Momentum, okay, we'll come to that. Some other formula that has mass in it. Kinetic energy. So I want you to, because that's what we are going to use for your lab. So you don't know anything about anything else about rotational inertia yet, except that it's similar to mass. Well, here's a place where mass has a role. Kinetic energy is given by 1/2 times mass times velocity squared. And I'm going to sort of trust this picture that I have been building, that there's a relationship between these two, there's an analogy between them. So trusting in that analogy, I have more reason to trust in that you guys do. I'm going to guess at this formula for rotational kinetic energy. That rotational kinetic energy is given by 1/2 times something that's analogous to mass, so rotational inertia, times something that's analogous to velocity, or angular velocity, and squared. So this is an expression formula that you are going to take as given for your lab. So starting with this, you are going to make some measurements, and using those measurements, calculate rotational inertia, and from the rotational inertia, see how rotational inertia might depend on other quantities. I have a sense it should depend on mass, but as you saw with the ruler, it's going to depend on some other quantities. And in your lab, you will measure that quantitatively using some specially made apparatus. So this is something called a rotational analog. I've been hinting at it since the beginning, but let me make it explicit this time. And this is really the reason I want you to start paying attention to this from the beginning. Because if you treat rotation as a separate subject from what you have been doing so far, it's just way too much information. There's no way I can memorize all that. But if you recognize the relationship between translational motion and dynamics to the rotational motion and dynamics, then there's not a single thing you'll have to memorize new. Everything that you saw in translation will just, by analogy, be transferred over to rotation. So let me write out this table for rotational analogs. So I guess, let me write down. Rotational analogs. So, analogs as in analogy. So let me write down a few basic quantities. So the reason we can do this now is we just finished covering rotational inertia. This is the last of the basic quantities that have to be defined so that any other quantity you can imagine in translation, you can essentially guess a formula in the rotational case. So in translation, we have the kinematical quantities: position, velocity, and acceleration. And we had, so these describe motion. And we had a question of, what causes motion? And what causes motion is force, right? And as you are introducing force, you actually have to define mass as well. You have to define inertia, because force is not equal to acceleration, it's only proportional. And the constant of proportionality is mass. All these quantities sound familiar? So I'm grouping them by, when we introduce them. So this covers all the basic quantities. And they directly correspond one-to-one to the rotational quantities. So there's the angular position, angular velocity, and angular acceleration, right? The rotational kinematics. And in the question of what causes rotational kinematics, what causes angular acceleration, our answer was torque. And as you introduce torque, you have to have a quantity that's similar to mass. And that's what we just finished introducing, rotation inertia. So that's the analogy, as in you can anything, so let me just draw the line of analogy. Anything that involved position, if we are thinking about the rotational cases, you can express it in a way that involves angle. So, if I'm talking about position of this, let's say distance, that this ball travels from here to over here, then I can express it as, all right, the radius times the angular position, right? So I can say this distance here is some r times the angular position, or invert that relationship and say this is x over r. So I won't write down all of them since I already did. So there's the one-to-one sort of analogy between every quantity here and every quantity here. Let me write it down for force and torque. So we don't actually describe force in terms of torque. That kind of seems backward. Force is the basic quantity, and from force we can write down torque is force times some displacement, or r, that's the radius of the circle that you imagine the point to be moving in, times sine theta. Good. Same thing, we don't really describe mass from inertia, but we can describe inertia from mass. And as we just covered here, actual formula is not, so it now starts to get more interesting, because inertia is not just going to be simply mass times some distance. It'll depend on geometry. So what I can say is that rotational inertia of a point mass, at least, will be mass times the radius squared. Okay? And what I want to remind you is that when we came up with this description of rotational inertia, we had a particular goal in mind. We wanted to make sure that this relationship held, that net torque is equal to rotational inertia times angular acceleration. And this expression is true, whether you describe it using this or whether you describe it using this. That's by design. And having designed the things this way means now we have an analogous relationship from what you have on the right-hand side, the translational quantities, to a similar quantity that would be on the left-hand side. So, after we've done all this, what are some of the derived quantities that we defined after we finished with standard strategy? What did we cover? We defined the work. So we said work is force times distance. Okay, any other quantities? Energy. We have a bunch of formulas for energy. I guess let me not do potential energy because that's all translational. I can do kinetic energy. So kinetic energy is equal to 1/2 mv squared. All right, any other quantity we defined? We defined the momentum. We said momentum is given by mass times velocity. Is that it? Yeah, we had the impulse, but I'm not as fond of impulse as all the other things. Work is necessary because energy doesn't have a definition. Work is how you describe energy. But I have a definition for momentum. I don't really need impulse. So anyways, okay, I think that's actually it, right? So we have these three derived quantities, the quantities that are derived from these basic quantities introduced. And what I'm telling you, what I'm claiming, and you can, this is true, is that for the rotational equivalence here, I don't have to derive these formulas from scratch. I can simply look at the formulas here, copy it over here, just converting each of these quantities into their rotational counterpart. So for example, let's say I wanted to figure out how much work am I doing as I try to rotate this from this vertical position up to this position. Let's say I wanted to figure out how much work I'm doing there. Then looking at this expression here, I would guess, all right, work I'm doing as I cause some rotational motion to happen, I would say, force, so torque. torque times displacement, so change in angle. So I have to say that. Yeah. And by the way, this is one of the reasons sometimes people get confused with the unit for torque. Unit for torque looks like a joule, unit for energy, because angle has the unit. But what I'll tell you is that torque is not given in joules. Joule is a unit of energy. Torque is always given in Newton times meter. We never express that as joule if I'm talking about torque. Okay, so that's work done when I'm causing some rotation to happen. Kinetic energy, so that's the translational kinetic energy. I can talk about rotational kinetic energy. That's a kinetic energy that this would have from rotation. Or sorry, it's harder to say. Here, so right now, it has to be in the air, so I'm going to throw it up. But ignoring this vertical motion, it has a kinetic energy from this rotation. Good? We'll have a demo that illustrates that. So the rotational kinetic energy is given by, all right, I see this formula here. Let me copy it over, converting each of the quantities to rotational version. What's the rotational version of 1/2? Still 1/2. It doesn't. It's a constant. Times m. So the mass is going to be rotational inertia. That's going to depend on what geometry you have. So let me just write it down as I. To fix down what it is, I have to know the geometry. Times v, so angular velocity squared. So this is the formula for rotational kinetic energy. And because we went through this trouble, this is, by design, this is guaranteed to be correct. And let me finish this up here with what we are going to call angular momentum. So let me just quickly write it down. Angular momentum, we use the letter L for some reason. And we are going to describe this angular momentum in a more fundamental way on Thursday. But let me write down another version that's based on this. So momentum is mass times velocity. So I might say angular momentum. Let's say I think it might be rotation inertia times angular velocity. And this is pretty close to true. It's true almost all the time. There are some exceptions that you can come up with, but that's what we'll talk about on Thursday. Good? Yeah?
I have a question about the work rotation. It's equals to torque times the angle, right?
Yeah.
But torque already has an angle, so.
Oh, yeah. I would have to be careful. So, let me not use theta here. Let me use phi. So, when you talk about the angle in torque, it's the angle between this displacement here and the force that I'm applying, right? So imagine I'm bringing this up from this position by applying a totally vertical force. Then yes, this theta will be changing as it goes from here so from something that's close to 0 degrees to something that's close to 90 degrees. Wait, that's very confusing. Yeah, but the angle that I'm talking about here, it's the change in angle here. So actually, I can imagine applying torque differently. Instead of applying a force here, I can apply torque near the axle. I can apply torque this way. So, in this expression, you don't even have an actual discretion of torque based on force. I would simply give you what the torque is to bring it up to here. And that torque times this delta phi would give you the amount of work you had to do. Yeah, so when you get into actually angular quantities, you do have to be careful because there are different things that can be rotating. So you have to be careful not to use the same symbol for different angular quantities. So I guess, the way I should have really done is I should have changed this theta with a phi because this theta is same theta as this one. But this phi is something that's defined in this specific context. Good? Yes? Yeah. It's like, if you have two different people named Andrew, it's not a guarantee that they are the same Andrews. So usually you try to call people by different names so that you don't get confused. Okay? So this is the rotational analog. One thing that this is very useful is, it's useful in two ways. One, it saves you the trouble of memorizing all these new formulas. Because if you had kinetic energy, translational kinetic energy memorized, then well, this is the rotational kinetic energy. You don't have to memorize anything other than this correspondence here. So it's useful in that way. And two, this analogy transfers over for your intuition as well. as in whatever intuition you had for energy, rotational energy is still energy. So, you have intuition that energy is conserved. Well, rotational kinetic energy is also conserved. You can turn rotational kinetic energy into other forms of energy. And you might have some intuition for momentum. And that transfers over to angular momentum also. So I guess that's where I want you to do a couple of demos so that I can illustrate some of that intuition you might have. Let me do a demo for rotational kinetic energy. Or this is a demo where the explanation of the demo would be possible with rotational kinetic energy. I'm just using this as a paperweight or bookstop or whatever. So let me set up an incline. There's a reason that this has been sitting here whole semester. We use this for some things. So here's my inclined table. And what I am going to do after moving things that break out of the way is I'm going to roll down these two objects, a ring and a disk. And they actually do have roughly the same mass. So let's say they have the same mass. Turns out whether they actually do have the same mass or not doesn't matter, but let's say they have the same mass so that you don't have things to worry about. So I have two objects, disk and a ring of the same mass. And this is the question. When I roll them down, starting from the same height, let me stop them with this. So I'm going to roll them down, starting from the same height, and they're going to roll to the bottom. So the question is, well, do they reach the bottom at the same time? Does one reach the bottom, faster than the other one? What do you think will happen here? They have the same mass. I mean, it doesn't actually matter because if imagine with the gravity, if I drop it, whether they have same mass or not, they'll drop at the same rate, right? So, but that's why I don't want to get confused by it. But let's say they have the same mass, but whether they do or not, it doesn't actually matter. Yeah, Sergio?
The copper one, the ring will reach the bottom faster just because of where the mass is.
Okay, so you are looking at how the mass is differently distributed, right? So I do want you to pay attention to that. So with this copper ring, the mass is farther outside. So I'm going to relate that to rotation. So in terms of rotational inertia, which of these two has greater rotational inertia? The ring, right? Yeah, larger radius for all of its mass. In fact, do you have a guess for what the formula for rotational inertia of a ring is? If I'm rotating it about by its center? Yeah, mr squared. So this is one example where actually all the masses are at the same distance. So you can just use the same formula as the formula for the point mass. It turns out, this turns out to work for a ring as well, as long as you're doing it about its center. So this says mr squared, and the rotational inertia of a disk is actually half mr squared. So, but you already have an intuition that this does have a smaller rotational inertia. So starting from that, this is what I want you to reason through first. Okay, so the ring has larger rotational inertia. All right. So this is how you'd analyze it using conservation of energy. Do they start out with the same amount of energy here? Yes, they start out with zero kinetic energy whatsoever and some amount of potential energy. So the second question, when they come down here, they have both zero potential energy. Will they both have the same amount of energy when they come down here? Let me restate the question. They started out with the same amount of potential energy here. After they roll down, when they are here, do they have the same energy? Okay, why yes, Ranjit?
Have no more potential energies.
Okay, no more potential energy, but I'm looking at the total energy. Do they have the same, Steven?
Assuming that is total energy is conserved, all potential energy returns to kinetic energy.
Yeah, so the key here is that does this setup look like something that conserves total energy? As in, you don't have things sliding with the friction. So energy is conserved in this setup. That's why when they roll down to the bottom here, they will have the same energy. They started out with the same energy. When they end up here, there's no reason for their energies to be different. Now, here's the situation you need to consider. When they reach the bottom here, not all of their energy will be in something we call translational kinetic energy. So translational kinetic energy is what you have been seeing so far. We haven't called it that because everything was translational. So there's a reason we've been using this card and not these balls. This card illustrates something that has translational kinetic energy and zero rotational kinetic energy. Because as it moves, everything is translating. And I mean, these wheels are rotating, but they are so tiny that there's very little mass and energy associated with it. Once you are looking at things that roll, it changes. As it rolls, a significant amount of its energy will be in rotational kinetic energy. Okay? So I'm trying to wrap up this end here. All right, so these are some of the facts that you need to put in consideration. They have different rotational inertia. This has greater rotational inertia. They have the same amount of total energy, both here and here. But at the bottom here, one of them will have greater amount of rotational kinetic energy. Which of the two do you think will have greater rotational kinetic energy? The ring, because you're looking at this. Well, if somehow omega doesn't change, then greater I would mean greater rotational kinetic energy. So let me flip the question around. When you look at the translational kinetic energy of both of them, which one do you think will have greater translational kinetic energy between them? The disk, right? Yeah, because this has to waste less energy, it has to put less into the rotational form. More of its total initial energy can go to translational kinetic energy. So that's the argument we are making. So the argument would be this should have greater speed by the time it reaches the bottom. Let's try it and see. I'll do it a few times. So let them roll down. Yeah, the disk does roll down faster. So let me do it a couple more times just to be sure. So yeah. So I swapped their position around so that in case anything that matter. Yeah. Sometimes the ring initially wins because it's a little bit distorted. It's not the exact circle. But over long enough of a roll so that you can average that over, you see the disk win over. So let me do it one last time. So ready, set, go. Yeah. The disk always rolls down here faster because its velocity when it reaches here is greater. So its average velocity over the thing is greater. It takes less time. Okay? So this is an illustration of kinetic energy or rotational kinetic energy. So by the time so they do it at different times. But when they reach the bottom here, they do have the same kinetic energy at the moment when they reach down here. But the difference is that the fraction of energy that's in rotational kinetic energy is greater for the ring than the disk. The last demos I wanted to do involves conservation of angular momentum. And let me just do the demo. I won't go into too much of an explanation. I will do that on Thursday. So let me do 2 angular momentum conservation demos. So you've seen this platform before. It's the one that rotates fairly easily without friction. So if I put myself up here and set mine to rotate, then dizzy. I do just to rotate, Okay, balance. Yeah, good. Nothing so complicated. And what I'm going to illustrate is how I can. I can make myself rotate without really touching anything outside. So, if I just do it this way, I can actually make myself rotate. And this actually is an example of conservation of angular momentum. So what do you see as I try to make my upper body rotate viewed from top, rotate clockwise? Like what do you see with my lower body? If I try to make my upper body rotate clockwise,
The opposite way.
my lower body goes counterclockwise. Why is that? Or what principle would you use to describe what's happening here? There's a little bit of friction that I can use to gradually rotate myself. Like, do you remember a principle that we covered in the translational motion? What was that? Yes? So conservation of momentum, but what was it a consequence of? There was another principle that we covered before momentum that led to conservation of momentum. Yeah, Newton's third law. So we can actually borrow the language for this. We can talk about action torque and reaction torque. So my lower body is causing, exerting clockwise torque on my upper body, but there's a reaction torque which is causing my lower body to rotate the other way. Yeah? So what I'm actually going to do is I'm going to take this wheel and make it spin. So right now I can make it spin without me rotating for a reason that we'll explain later. And so right now this wheel is, viewed from top, it's not really rotating. Because when you view it from top, well, it's rotating the other way. So I'm going to turn this wheel in a way that the wheel turns clockwise when you view it from top. So then you see, what direction am I rotating? Yeah, I'm rotating counterclockwise. So, so if you look at the angular momentum of the wheel, right now, viewed from top, you would see something that's like a zero. And when I exert torque on this wheel to give it a clockwise angular momentum, there's a counter torque on me that's causing me to rotate counterclockwise. Good? Or if I cause this to rotate counterclockwise, then there's a clockwise torque on me, causing me to rotate, this way. Good, that's one. I thought I had one more demo. Oh yeah, I have one more demo that kind of needs a volunteer. So I need a volunteer because it can be dangerous, but that's not the reason. I need someone to spin me. So this is actually something you see with angular momentum that's not quite easy to see with translational motion. So this is what I'm going to do. I'm going to start out with these masses outstretched. So when you look at this expression here, rotational inertia will be large. And then I'm going to bring this mass in, reducing my rotational inertia. What do you think will happen with my angular velocity? Did I hear decrease or increase? Increase if the angular momentum is conserved. So the volunteer I need is, I need somebody to spin me because it's hard to spin myself outstretched. Can someone spin me in a gentle way? Somebody. Anybody. Ranjit, come spin me. I'll tell you when it's too fast.
This way?
Either way is fine. I think I'm used to going counterclockwise. So,
Okay.
no, my arm is easier, yeah.
Okay.
The other way, yeah.
This way?
Yeah, okay. A little bit faster. Okay, a little bit faster. Okay, I think that's fast enough. All right, so I'm going to bring the mass in and watch. Yeah. So this is an example of conservation of angular momentum. And actually, you see figure skaters do this. When they do the whatever axel jumps, they so as they are jumping, they have their arms outstretched, and in the air they bring it in to spin faster. Good. Okay, that's easy. Thank you. All right. So I guess we don't have any time for cross product. So let me just do a demo that's supposed to lead to that discussion. So what you have seen is conservation of angular momentum. So why do you think angular momentum was conserved in the two demos you have seen? So for the answer to this question, you want to think back to what was the condition you needed for you to say total momentum is conserved. What was the condition? Not work, that's energy. External. What about external?
There's no
Yeah. So the more precise version was no no impulse due to net external force. But it's the external force that you are worried about. So with angular momentum, it's going to be the same thing. It's the torque due to external forces. That's why it was important that this was rotating frictionlessly. You can actually get a situation where angular momentum changes. So if I hold this from this end and let go, there will be torque due to gravity. Gravitational force acts here, pulls it down, and swings it down this way, right? I mean, I don't have to do that for you to be convinced that that's what's going to happen, right? Now, the motion that you will see is something called a precession. And this is the one that really requires us to handle rotation like the vector that they are. That's where we are going to need to use cross product. Now, when I let go of this wheel, it'll do this motion. Maybe you have seen it in different other classes, but otherwise, this is a quite unintuitive motion. And this is difficult to describe using any other tool than what we are going to introduce, I guess, on Thursday. Dealing with all these rotational quantities as actual vector quantities. Because this is what I wanted to point out, but I ran out of time. So with the translational quantities, you have seen me meticulously draw these vector notations, right? Vectors. And with the rotation, I haven't done that because we haven't treated any of these rotational quantities as vectors. But what I am telling you is that there is a way to describe all of these, well, not this, all of these as vectors. And we are going to introduce the mathematical tool you need to do that. And that will be used to explain this precession that you just saw.
Hi, in this video, we will see examples of angular momentum conservation. Angular momentum is related to torque in the same way momentum is related to force. That is, just as you need to apply force over a duration of time to change momentum, you need to apply a torque over a duration of time to change angular momentum. And just as force obeyed Newton's third law, when two objects within a system interact with each other, there's no net change in momentum because the impulse due to the action force is cancelled by impulse due to reaction force. Torque obeys Newton's third law. I can illustrate this best with this freely rotating platform. If I stand here and try to rotate myself, that's just like trying to move myself on a frictionless sheet of ice. You can't, because as the upper body is made to rotate clockwise, the lower body rotates counterclockwise because of the reaction torque. But here's an interesting twist. Just as I can move myself on frictionless ice, if I have some object to transfer momentum to, like a wall to push, or someone else to push, if I have some object to transfer angular momentum to, I can make myself rotate the other way. Here, I am holding a wheel spinning clockwise, as viewed from top. When I flip the wheel over this duration of time, on net, I am applying a counterclockwise torque on the wheel, which ends up spinning counterclockwise. And as I apply counterclockwise torque, the wheel applies a clockwise counter torque on me, which causes me to spin clockwise. If you consider the system of me and the wheel, the total angular momentum is conserved. I am spinning clockwise fast enough to balance out the wheel's counterclockwise angular momentum and some more. And this is because there's no net external torque on the system. Another way angular momentum can be conserved is if the applied torque is zero. And you can have zero torque with non-zero force. If you remember, torque is force times lever arm. This is what causes things to rotate. A good example that'll provide a useful mental picture for later is orbits of planets and asteroids. This is a typical planetary orbit. It's pretty close to a circle, and you can see that angular momentum is conserved. It's going around at a constant speed, but not very interesting. Let me show you comet-like orbit. These highly elliptical orbits simulate orbits of comets, and angular momentum is conserved here. The torque on these comets as they orbit is zero always. The gravitational force from the star, central force, pulls directly towards the star. So there is no never arm, no force perpendicular to the displacement that tries to make the comet orbit more or less. But when the comets slow down, how can we say angular momentum is constant? Well, angular momentum is rotational inertia times angular velocity. So when the comet gets farther away, its rotational inertia is increasing. So if its angular velocity decreases in just the right way as this radial distance increases, then the angular momentum of the comet will be conserved. And that's what happens. Johannes Kepler described this observation in the Kepler's second law of planetary motion. A planet's orbital speed decreases as it moves farther away from the sun in its elliptical orbit. Today, with the help of classical mechanics, we can see that this is a result of conservation of angular momentum. While we won't spend much or any time working out orbital mechanics, I want you to remember the angular momentum that is associated with orbital motion. We are going to call back to this when we cover quantum mechanics in Unit 4 and a strange assumption that a physicist named Niels Bohr made regarding angular momentum. There is much more to say about angular momentum and torque. For one, my treatment so far in this video ignored the vector aspect of torque and angular momentum. With torque and angular momentum, the direction matters in the full three-dimensional sense. This sense of direction is assigned using the right-hand rule. I will leave it for the videos assigned for your Chapter 2 essay assignment to cover additional implications for this. For now, what I can say is, when I was describing this wheel as spinning clockwise, what I really meant to say is its angular momentum is pointing downward. And in order to get it to spin counterclockwise, I applied an upward torque. But be careful, upward torque is not the same thing as upward push, which is why I'm leaving the full discussion of this aspect to another video. Please give the rest of the chapter a try and let me know if there are any remaining questions. Bye. Yeah.
I don't
So
know.
let me do this, especially for the benefit of the people who might be watching this video on the recorded version later. So what I want to show is the, because this 4-minute video, it is worth watching over multiple times until.
Yeah, I watched it like 4 or 5 times.
Good, yeah.
And I thought I got it.
Yeah. And there's a lot of information that's here. So here he's describing the force that he's applying.
Right.
This is what we call lever arm, and he gives the direction of torque. So here's the kind of unintuitive thing. Torque is a vector quantity. You can associate an arrow with that torque. And so that's what he's explaining there. And he'll kind of explain his way there. Let's see. And yeah, here he's saying that that results in torque coming out, and that's what's called the right-hand rule. And
yeah.
let me see. And here what he's showing is that there's in the same way he associate a vector quantity to torque, you can associate a vector to angular velocity. So as this is spinning, there's an angular velocity that's a vector, and this increasing arrow is what is showing is that increasing angular velocity.
Yeah,
or he might be saying angular momentum. I don't know for sure. Yeah.
right. So I'm sorry. So right here, so this red arrow,
Yeah.
what exactly does it represent? And if it's a vector, you said, so I said it's of angular momentum, right?
You can say angular momentum. Yeah, that's fine.
But it's not a torque because the torque is what he applied, correct?
Yeah, let me write down the related mathematical expressions, which, because this is where it gets mathematical, so it's worth keeping the formulas in mind. So I have, so this is something he wrote down earlier, torque as a vector,
Yeah.
lever arm as a vector times cross product with the force.
So yeah, radius multiplied by force,
Yeah, and the relationship to keep in mind is angular momentum. Oh, sorry, my torque there's, well, I focus on that. Angular momentum, which is given by L. L is the letter we use for angular momentum. It's related to angular velocity this way. It's related to angular velocity by rotational inertia times the angular velocity. And here you do use the vector quantity there. And you can also relate this angular momentum to linear motion quantities this way, in a way that's looks similar to this. Sorry, let me change my pen color. I don't know on his forehead how this also. Oh wait, that's all right. I don't know why I picked the skin color. All right. Well, that's still not good. Maybe this. Yes.
So really quick, this red arrow is the angular velocity. Is that what it is?
Without actually listening to him speak, I don't know which one he is using. So let me write the. Actually, you can see it from the expression I've written down. This expression here. So whether this arrow represents angular velocity or angular momentum, the diagram-wise, it doesn't matter because they are proportional to each other. So the only difference, if he were using angular velocity versus momentum, the only difference would be this the scalar vector that changes how long the arrow should be. So that's why I'm saying it could be either. It could be like angular momentum. It could be angular velocity. So for this angular momentum, it can be related to this quantity here, the lever arm cross product with momentum. And this is the similar relationship in which, so the kind of to get a handle around the vector idea of angular momentum, you want to kind of connect it to the torque because there's a very close relationship between these two. You had a question?
No, I think that's fine.
Yeah, so here's where he describes that vector aspect of angular velocity or angular momentum, and showing how that increases as the rotational speed or the angular momentum increases. He's showing that. And then...
Because honestly, physically, on a physical level, I still trying to fathom it. You know what I mean?
Yeah, I recommend that you don't do that.
Okay.
Here, because this is highly mathematical content. If you're trying to use your intuition will fail you. That's why we don't get into this mathematical content for physics 10. In physics 4a we do, and what we heavily rely on is the fact that people there can do vector math. They are supposed to be able to do vector math.
Okay.
Yeah. So rely on the math. That's really what I would encourage you to. So this is where he's describing the torque due to gravity, and so that torque due to gravity has different impact. When this is not spinning, the torque due to gravity causes this to spin down, and what that amounts to is, well, there's an increase in angular momentum that's coming out of the screen.
Yeah,
And-
that part I understood, right?
Yeah. And when it's pre-spinning, and this is where I was saying the explanation you are giving is fine, that's good. Is that if this is already spinning, you have angular momentum coming out this way. And torque, it leads to change in angular momentum. So this is the mathematical relationship between the two that that we won't be able to get too far. Is that torque? So oh, we had this. We had this from chapter 6, I think. That force is the rate of change of momentum. I think we covered that much. Force is, yeah.
That's
In a
fine. So,
similar way, torque is the rate of change of angular momentum. Or another way to express this is to say that change in angular momentum over some amount of time is given by torque as a vector quantity times the duration of time.
right.
So the torque due to gravity is going to result in change in angular momentum, and you will have an angular momentum change that's coming out of the board. And when you already have a vector that's pointing that way, this change that's in a perpendicular direction from the original vector causes the vector to rotate a little.
Right, right.
Yeah, and that change kind of it causes the angular momentum vector to change in a horizontal direction. So, yeah.
That's fine. Sorry, didn't mean to take so much time on this.
Yeah. So no, but this is the reason I give this to you in the essay assignment is because it's an interesting concept. It's something that I want people to kind of look at it, struggle through, try to understand it, and this does come up in I think some of the exam essay questions. So it's worth making sure you understood. And yeah, but in terms of kind of being able to fully explain and fully understand everything, I do want to caution you that this material gets mathematical, and at some point you might end up having to say that all those arrows, it's too much geometry, and that's fine. That's why nothing that I do in this class will require you to reproduce all that vector argument, because that's a physics 4A level material.
Thank you.